Hello everyone, this is the review of last lecture on deep learning. So the revival of neural network type approaches started around 2010, and these three guys were instrumental: Jeff Hinton, Yann LeCun, Joshua Bengio. And Hinton in 2013 gave this nice list of components of deep learning. So you should take a large data set, in particular if you want to train a new application from scratch, and if you cannot use a pre-trained model. We discussed this during the lecture. Take a neural network with many layers, maybe 7 or more, and large layers, maybe 1,000 nodes per layer. Nowadays most of the computing is using GPUs or GPU cluster even to speed up some of the essential calculations. Then training is done by stochastic gradient descent or a smart variant like Adam. So this is nice that we can take over this algorithm for training, which we are already familiar with. Then, except for the output layer, use rectified linear units, where the response is 0 if the input is 0 or smaller than 0, and for inputs which are activations which are larger than 0, it goes linear with h. Then regularize with dropout, which is a new way, new alternative to weight decay or to stop training. Optionally initialize weights with unsupervised learning. This is not done so much these days, although unsupervised learning is by some considered the key to really achieve human-like AI. And use convolutional networks, and max pooling is if the input is spatial or a picture. And so this was 2013. There are a few things added, and we cover that partially today. For example, recurrent neural networks turned out to be very powerful. So then we went through these different aspects, and I gave you some finer details on some of the issues. Backpropagation is applied, the algorithm we learned about in the last lecture on the neural networks. Just that the backpropagation is propagated through all the layers, from output to input. So the error goes through the layers, and that's why it's important to have these linear units, these rectified linear units, because the gradient nicely propagates the linear layers, but we need the nonlinearity to get the real power of neural networks and exploiting the nonlinear behavior. So one special neural network architecture we discussed are the convolutional neural networks, CNNs, sometimes also called convnets, and they're very powerful in vision applications. So this is a typical example. You want to recognize handwritten digits, and so I went through these different historical developments, but essentially a layer. So there's one layer for each filter kernel on this level here, So each of these layers has a specific filter kernel, which looks only at a certain region in input space. Then this location is shifted through space, and then this window also moves accordingly. So it has a local receptive field, and all the receptive fields for neurons in this in this area here are the same. And then here's the same thing, only with a different kernel. And maybe you have even several layers of these convolutional layers. And that was key to getting these great performances in vision application. So that was really absolutely key. And the important thing is that you get very good test set performance and only almost no overfitting in these type of problems. Yeah, so these are all details. Yeah, ResNet is a very deep architecture with 152 layers, which is quite popular. Then you can also train convolutional networks to decide on these bounding boxes around objects. And yeah, we discussed these adversarial examples where by disturbing an image in a very particular way, so this is not a random disturbance, you get something which looks to the human eye identical, but for deep neural network might look like something completely different. And yeah, this is still a challenge today. And one explanation, which I think is quite fitting, is this idea of the manifold, that the training data is on a low-dimensional manifold. We discussed this earlier, and if the test data is not on the manifold, the prediction might not have high quality. So why does it work so well? I like this work by Tommaso Poggio and co-workers very much, and and he analyzes three things. First, approximation theory, and he introduces a new class of function, the compositional functions, and he got this result. So I added this table here, which I think summarizes very nicely some of the issues in neural networks. So with if your target function is only characterized by some form of smoothness, and you're using fixed basis functions, then we have this exponential increase in number of parameters. Or so if you use allow an error of 0.1, this becomes more intuitive. So it's 10 to the power of large M divided by small m, and large M is the number of inputs, and small m was a measure of smoothness. And you can look at the Poggio paper I cited. Then if you use a function class, target function class, based on this complexity measure CF, introduced by Andrew Barron in his work, and you use neural networks, the number of parameters is m divided by m square times 4 divided by epsilon. And if you put in the 0.1 again, it's 40 times large M divided by small m square. But the smoothness is not defined in the same way. But still, I think, I mean, it's an amazing improvement here. The M comes in when we discussed Barron's work. We looked at the number of hidden units, but of course, there's a huge number of parameters from the input to the hidden. So you have to multiply his number by m to get the number of parameters, at least in the order of notation. So it's 40 times number of inputs divided by m squared, and that is a very different scaling behavior than with fixed basis functions. And if the target function is compositional and your model function is a deep neural network, then again by plugging in this number we get 100m divided by m squared. So it looks very similar to Barron. Again, the smoothness is defined slightly different in Porteous in this approach here. But yeah, so it's nice to see that for neural networks or deep neural networks we have this really nice scaling behavior. No, it's not 100% comparable because the smoothness definition of smoothness is slightly different, and also because the model classes are different. One was CF, and for the second result it's compositional. But the linear increases in M, or only linear increase in M, is very comforting, and this is a really nice result. And I think Porteous analysis gives a lot of good insights into the problem. And then the second one was the optimization problem. Why does optimization work? Why aren't there more problems with local optima? And the general assumption is that it has something to do with it, that these minima degenerate and take up a lot of space in this parameter space. So there's a high likelihood that it finds one of these deep degenerate optima, which are all very good, instead of falling in a maybe very local bad optima, which is doesn't have this good performance. And then, the last thing is the how many data points do we need for having good generalization ability, and also he gets nice results because of this effect there's only one real parameter. The second one is redundant, so the number of real parameters or effective number of parameters might be much smaller than the number of parameters in the neural network, and this also is good for good generalization performance. So instead of number of parameters divided by n, you can substitute number of effective numbers of parameters divided by n. Okay, and the LMU is also offering a lecture on deep learning. This is going to be in the winter semester again. But why is this a lecture on machine learning and not deep learning? Because if you're only focusing on deep learning, you get maybe too much tied into all the nice tricks and heuristics and focus extremely much on performance issues, and maybe if you want to go in a startup in the performance in the real world, but you lose some of the nice theoretical backgrounds, and of course also deep learning is not always the right thing to do, although it's currently a high-performing approach. Okay, so thank you very much for the attention on the review.